Good afternoon, everyone. I'm WCTR, Associate Head in Department of Civil Engineering. Today, we are very happy to have Professor Hong Kelo to give a presentation here in this series, HKAE series, right? I'm sure most of you know Professor Hong Kelo. He is currently the Dean of Engineering in HKUST, also the Director of Smart Institute. So I don't have to close the. Actually, he is the director of Great Smart City Institute. He actually has a very long CV, so I don't plan to read it all. You can have a look on this. Basically, he is the fellow of many institutes, including fellow of HKIE, fellow of HKAE, fellow of Hong Kong Society of Transit Study, and also fellow of CILT HK. So more importantly, he has many students. One of his student is me. I'm his first PhD student. So if you want to be very famous in the future, you better contact Hong Kelo to become his postdoc or his colleague. So without further delay, I would like to invite Professor Hong Lo to give his presentation. Thank you, Professor Hong. Hong Kelo.
Thank you. Thank you very much. I want to spend some time, I promise, less than 40 minutes, so that I save some time for interaction, for Q&A. This topic I've been working on for a long time. I published the first paper in 1999. So I always thought about, and I came back from the US, I thought I should develop a system that the government can use. I want to actually have my work implemented somewhere. So I came back, and after 20 years, and Hong Kong has changed. For the last 5 years, there's tremendous funding. They're also government very open. So I got to try my system implemented in Tung Chung first, and to many applications I'll talk about. So I think Hong Kong in the last 5 years had tremendous funding. For those who get a smart traffic fund, so it's funded by smart traffic fund a few times. So the total funding, I wouldn't say, but not small. More importantly, is because Transport Department is very open now. So I convinced him to try, and they try. In the last 99, don't even think about it. So it's actually for the better for Hong Kong that we actually have this system now. So what I'm going to do is advanced AI-based adaptive dynamic traffic control. I added a subtitles from theory to applications. So how do I make the theory published in 99 and quite a few more papers afterwards, and make it now a system that we can actually benefit society in real terms. So traffic signal, I like to look from a historical perspective. The first signal was debuted 1868. So how many years ago? More than 100 years for sure. And then people always thought we are done with traffic signal. We have done enough. The topic is done. So when I start looking at that, and I disagree. So traffic signal is among the most cost effective because it doesn't need construction, doesn't need any infrastructure, building a bridge or a tunnel. So it's very cost effective. All you need is a very smart system to handle traffic conflicts. So therefore, I always thought this is a good topic, especially in the era of smart city. This could be a low-hanging fruit. Instead of thinking about something very big, think about something we can do tomorrow, which is traffic signal control. So that's why I started the topic way back. So if you think about Hong Kong used two systems. One bought from Scoot is from the UK. SCET system is bought from Australia. These two systems are proprietary. They lock up the system. They don't want anyone to look at them. So if you want to change the system, fly someone from UK, Australia to fix it. And then I charge very high rate. I think this is not the way to do things now. We talk about open system. We talk about making open architecture. So I always thought to Transport Department, let's, in the next era, let's make it open. Buy controllers not from UK, not from Australia. There are plenty of those open architecture from China. And now there are two approved types of controller. Hopefully it's open architecture so anyone with a good idea can tap into it. This to me is very vital for Hong Kong's future. And I think they agree with this approach. So in the northern metropolis, CEDD thought about how do we how do they bring in open architecture, open system into Hong Kong. I think this is fantastic. For anyone working on this topic, you can try your algorithm without flying someone expensive from Australia or London. So that's that. If you want to take a look, most of the Hong Kong urban areas are equipped with either SZETO or SCETS. So those are the two systems used in Hong Kong. So eventually, I hope we can break we call jailbreak, right? We can jailbreak this two system. Actually, we did. That's how we try in Tung Chung. We have to find very difficult way to jailbreak SCET controllers. So we can implement our control algorithm in a SCET controller. Did a lot of work to bypass the SCET controller, so which is not a fun thing to do. So anyway, so this is the current practice. Now what I'm going to do is talk about some theory first before I talk about applications. Now if we want to do traffic control, fundamental traffic control, you have to capture three very elementary but very important characteristics of traffic. Number one is traffic varies over time. We all know that. It's not constant, it's not always the same, but dynamics change over time. So if you want to do a model right, you have to capture traffic dynamics. That's number one. Number two is a spatial queuing. Professor SZETO and I worked on this problem 20 years ago. So if we want to do traffic right, we have to make sure that we capture the spatial queuing property. I'll show you a diagram to mention about what is spatial queuing characteristics. Now this thing is fundamentally important for Asian cities like Hong Kong, Thailand, and so on. There's queuing happens horizontally, not vertically. I'll show you a diagram. For very short urban streets like Hong Kong, Thailand, Macau, you can think about Asian cities, spatial queuing model is fundamental. If you don't get the model right, don't think about you have a good traffic signal control, which is implemented in SCET and SCUT. So you can think that why we are not the wise investment to stick with these two, because they are outdated. One is developed in the 80s, one is developed in the 90s. It has been 30, 40 years ago. Their time has come for a new type of controller. The third is actually more complicated. It's called stochastic. Now, traffic arrivals are random, and they cannot be predicted perfectly. You assume the world is deterministic. You can have perfect forecast. You're totally wrong. So how do we capture dynamic, which is time, spatial queuing, space, and also random arrivals into the framework is fundamental. So the team and I have been tackling this three over the last 20 years. And then, so those are the theory part. So if you think about the current practice is to develop a fixed timing plan. So the timing plan, the green time and red times run like a fixed cycle. So 10 seconds of green, 30 seconds of red, and go back. It's a cycle. So the cycle works like an alarm clock. 8 o'clock in the morning, this plan. 9 o'clock, another plan. So you can store maybe a set of 12 plans, 16 plans, depends on time of day and day of the week, to adjust the timing, adjust for the different types of traffic. So that is what we are doing now. Now, of course, they use a concept called delay formula. I won't step inside. They use a DD1 formula for those in queuing, or MD1 or the MM1 queuing model. So they make queuing delay a deterministic formula. So even though they said stochastic, the delay is actually fixed by the formula. And they use that for calculation of a timing plan. Of course, we know that the assumption of steady state is questionable. Whether traffic is in steady state we know that it's not true. So when we rely on those theories developed in the 50s and 70s, we are bound to have not very good performance. So we have to get rid of this steady state traffic kind of mindset. Now, this is a very important thing for Hong Kong. So I point out point queue versus a physical queue. I think this is written by Professor SZETO. Remember that? This diagram, long time ago. Now, point queue is basically, this is a signal, traffic queuing stack up, because they assume vehicle has no physical dimension. They are a point. A point has no dimension. So you can imagine the vehicles are stacking up right in front of the traffic signal. And so why is that important? Suppose the blue vehicle want to make a right turn. The point queue model will say, no problem, make a right turn here, because the vehicles are all stacking up here. And the physical queue will be, in reality, traffic will go backward, queuing. So it jam up the roadway this way. So if the blue vehicle want to turn, they cannot because it's blocked. So this is a very fundamental difference between point queue and physical queue. So we want to do traffic control right for Hong Kong, for Asian cities where the block size are typically short because it's good for walking. US, the block size is very long. Why? Because they're driving. They don't care about very short blocks. So for any walkable city, the block size are typically smaller, like Europe, like Hong Kong, like you go to many Asian cities. They're designed for walking as an important component. The block size are typically short. That means they would not allow this thing to jam up. In Hong Kong, they jam up the junctions. So this is so important for Hong Kong, Asia. So that is the first motivation why I did the research back in the 90s. I thought this is not right for Hong Kong. I mean, this model is not right for Hong Kong. Simple, but not working. So if we want to do it right, now how can we do it right? So we have to go back to a set of models called kinematic models. So it works like this for those in fluid mechanics. It's a very familiar, it's a conservation condition with a fundamental diagram here. Density is here, and then flow is here. So density is a vehicle per km. Space is capture. Flow is vehicle per time, so time is capture. So when you capture both time and space explicitly, you get the physical queuing right. Now the only trouble is that this model is very hard to solve. You can solve it for a homework example, a small highway. When you want to solve it for thousands of streets, this problem becomes not possible. So this thing was developed in the 50s, actually. And realistic, practical computational technique was only happening in the 90s. And so this thing was in the books for a long time, and nobody can crack it. Right model, good feature, capture kinematic. I show you a diagram, but it's very hard to solve. So in the 90s, so my mentor, Professor Danganso at UC Berkeley, thought about one way to crack the diagram. He called this a cell transmission model called CTM. So this thing, of course, simplified the diagram. This is the uncongested side. This is a congested side, so red and green. So we approximate that by 3 terms: uncongested, congested, and the capacity. Any roadway with a capacity. So he developed a numerical scheme, which is very stable to solve it. He called this a CTM. So this is the equation. So you break it into the uncongested side, the green side, and then the congested side, the red side, and the capacity side, and then break the network into cells and look at the flow from one cell to the next cell. So control this flow using this equation. Now it looks complicated, but actually numerically it's very simple. You can solve it in Excel. You think about an Excel, you solve it there. So it provides very efficient computational technique to solve big networks. So this is what we did. So he published paper 94, 95. I talked to him a little bit because we were in the same department at the time. So I thought, wow, this thing is very good for traffic signal control. This is basically your control. Change your capacity while keeping flow, spatial queuing intact. So I thought about, wow, this is cool. So I went back, and then I came back here in 96. 96, I had no student, no funding. Unlike the people here, they get millions of startup funding. How much startup funding I got when I came back in 96? I got 100K. Good for a few trips to the US, that's it. So when my first student came, I have no money to pay for his tuition. So I begged the department head, Wilson Tech at the time, could you pay for my student? So this is how tough life was in the 90s. So 0 startup, no student would come because Hong Kong didn't have the research culture. Who would do a PhD in Hong Kong, right? People say go elsewhere. not here. So very hard to get students. Fortunately, Professor SZETO has a different mind. He joined my group 98 and then graduated, right? So he is a very special. He has a different mind for sure. Anyway, I coded this thing and make it a traffic signal control. Don't talk about the details, need some coding. Now I want to show you what is shock wave and Q spillback. Imagine traffic is going down the street here. This is the junction, and this is time. When the red light traffic queuing go back, the darker the color, the higher density is traffic. So you can see the queuing is going backward. We call this a backward wave in traffic. And this is another wave. We call it release wave. When traffic eventually, the red light is over, green time, traffic move forward. So you capture the backward wave, the forward wave, and the whole set. So you can see the traffic queuing is moving upstream, we call it. Traffic is going this way, the queue end is growing backward over time, which is exactly what we see in the traffic signal. Imagine traffic signal, the traffic queuing, traffic going this way, the queue is going backward, right? So it's exactly capture that. Now, moreover, if your green time is not enough, you can see the traffic queuing is actually accumulate from cycle to cycle. So the queue end become longer and longer, eventually jam up the whole street if you don't have enough green time. So this model captures the essence of spatial queuing with time. So this is a very important part. And then now we have a efficient solution to solve it. Okay? So it's no longer theoretical anymore. We can actually use it to real implementation. That was 99. Now, the next thing, which is harder. Harder is the stochastic arrival. Now, stochastic arrival, traffic arrives stochastically because of uncertain demand, uncertain time. So how do we handle stochastic arrival? Now, in the old days, people built a steady state queuing model. For those in queuing, you know, MM1, MD1, using a queuing model to capture the steady state delay. Delay in the model does not change, which is not right. So we have to capture the problem from first principle. So there are two ways. One is a robust optimization. Basically, look at the distribution without knowing the distribution. We look at the worst case scenario of this thing. Typically, this plan is very conservative, so may not be very efficient. Okay, you want to cover the worst case scenario, give everyone a lot of green time. Okay, if there's a sudden surge in demand, no problem. My green time is enough. But then long green time give a long delay. So that is not efficient. The other way is capture random arrival into a stochastic programming framework formally. So that's what we did in the last number of years, maybe 10 years. So the idea is we put this into a two-stage stochastic program. So stage one is to find a fixed, robust plan. And then here, stage two is the queue-based adaptive plan. So two have interaction. I explain a bit more. So this plan is a robust plan, meaning I can handle uncertain arrival here. Now, in case the uncertain arrival is not according to what I had calculated, I adapt it, change the plan. So we call this is a two-stage stochastic programming. Stage one, find a fixed, robust plan. Stage two, adapt based on the real-time information, change it. So and these two have interaction. I'll explain it. So this is what we did, and incorporate CTM inside this stochastic programming framework. Now, I promised 40 minutes. Let me speed up. How to calculate, right? How do we solve this stochastic programming? Now, stochastic programming is hard to solve. We know that. So in another study, we came up with a way to cut the problem into two parts without the problem size grew from cycle to cycle. The idea is, basically the idea is how much green time I need to clear the traffic without overflow. That means the green time is enough to clear the rivals. I call this phase clearance reliability. Now you can think about if I give people a lot of green time, sometime more, sometime less. Let's say I plan for a very high arrival. So green time is always enough. So this is high clearance reliability. Now the downside is if the traffic is not high, then I'm wasting all my green times, right? The green time does not serve anyone, it's a waste. So I want to find a balance between how long the green time ought to be first in stage 1 versus if my green time is not enough, I have to do adaptation, meaning I break the cycle, I break a lot of things, so which is not good. So what I try to do is find the optimal fixed screen time. So the balance between reliability of clearing traffic versus not have to adapt all the time. So I'm trying to balance this thing. So I call this the PCR approach we developed. I think we published that 2006, some time ago now, the PCR definition. Anyway, now those are the theoretical things. Now to make life implemented, make the system, the ball game is totally different. I learned that in the last 5 years. The real hard work begins. The theory, you can cook it up in your lab, right? Dream about the equations. But when you go outside, you're under a lot of constraints. I mentioned some of it. So the real work is hard. So this part we did. We built a stochastic program that incorporates CTM. Now what we need is a very efficient computational technique. And we need to calibrate the model using real data. We need a good graphical user interface so we can code communicated networks. So we don't want to do a lot of difficult coding. We need to find out what are the measures that are important, not only to calculate, but measure them. How do we measure your performance is great? And then we have to think about the decision on timing plan. And then area traffic control, how to work not with one junction, but many junctions in the same area, like Mongkok has easily 30, 40 junctions, closely related. And finally, how do we use optimization analytics to speed up the process so that it becomes real? So I just want to quickly go through some idea. So this is a stage 1, robust control. And then we use a reinforcement learning as stage 2 to link into stage 1. We use adaptive control, but a deep reinforcement learning model to link the two. So there are 3 hierarchical control framework. One is demand clustering. So we collect data, and then we use AI to cluster them into different groups. For different groups, we want to develop a different robust plan. And according to the robust plan, we have different event trigger, adaptive control. So the 3 are linked together. So this is the system. I won't step too much time here. So each layer requires further data usage. So the system, if you want to go to event trigger, you really need real-time information, second-by-second information. If you want to do robust-based control, you need a lot of historical data to develop the robust plan. So you can, depends on the cost effectiveness, how much money you want to invest. If you say, I have a lot of historical data, but I don't have money to do the real-time system, stop at layer 2. We give you the robust plan, which is good, much better than what they have outside. If you, on the other hand, you have resources to do the real-time control, go to the next level. I'll show you some of the examples. Using camera, using LiDAR to get real-time information, and then adapt the system in real time. So that's a layer 3. So this is other diagrams. Typical, this is a deep learning diagram linked to, this is think about stage 2 in the stochastic control. This is a stage 1 in the stochastic control, and then we link them together. Okay, so it will be published somewhere, I think. It's a paper that we published. And then we also exercise rolling horizon implementation. So the question is that how long you want to look ahead, and also how long you want to implement your cycle. So we look ahead, let's say, in the calculation, we look ahead 5 cycles of inference, and calculate 5 cycles of timing plan. We'll implement the first 3, and then rolling horizon. So each time we calculate, look ahead more than what we implement. So we also implement this rolling horizon implementation, all because of computational time and resource. So we are very careful. So this is a disco system that we developed. So think about this actual traffic. We have a system of surveillance, could be LiDAR, could be infrared, could be camera. So, and then typically in a normal junction now, they go to the signal controller and loop back. This is a very simple actuator control. So loop detector, camera, is there a vehicle or not vehicle? Very simple. So this is we call it actuator control system. Now, what we introduced to the picture is this system called Integrated Disco Software System. I'll give you a name later. What is Disco? So we send the surveillance data into cloud, and then the cloud, we use this optimization analytics through cloud, and then we will calculate the plan. Before we calculate or implement the plan, we send it to a vSim simulator. We want to make sure that the results are as real as possible. I'll show you what is a vSim, very detailed microscopic. So we validate with the vSim simulator before we kick it back to the controller. So this is our loop here. So we add cloud computing, cloud database, analytics here, and then simulator link to here. Before we implement, we want to make sure that the timing plans are sensible. I'll show you some diagrams. So these are some of the detectors we use. This is actually mostly used in the Dongchong area. We can use an optical detector using video, basically. And we can use a thermal sensor. Thermal sensor in the early days, people worry about privacy. They say, I don't want to see people's face. So no problem. We can work with a thermal. So in the thermal, you can see that you don't see the license, you don't see anything, but you know that that's a vehicle. So we work with a thermal sensor, or you can use a LiDAR. So we work with all sorts of intelligent sensors. Of course, you can use loop detectors in the old days if you want to. So those are. So this is another diagram. This is the first case study, which is implemented now for those who live in Yunnan. You know that this is helping you a lot. This is a Bok Oi roundabout, the first signalized roundabout in Hong Kong. I heard that a lot of people love the system now. If you live in Yunnan area, Bok Oi area, the traffic delay drop easily 40%, 50%. So this is one of the first study. So this is 3-4 years back. We fly drones up and send the data into a video analytics. You can see track every vehicle. And here is the second example. It's implemented also. This is Long Fu Lo. It's actually Tuen Chek, Long Fu Lo goes to the airport. And this round has a lot of trucks. We use the same. So we track all the vehicles here, look at their turning ratio, look at how they perform in the roundabout. So we collect all this data over time, which is very helpful to build up the demand clustering. So that's the input part. This is our model coded. So you can see this is a DISCO model. Have I said what is DISCO? It has a name. Oh, this is a DISCO name. Dynamic Intersection Signal Control Optimization, DISCO, DISCO system. It's actually a trademark now. So this is a DISCO coding. Now we can do automatic coding. All you need is to give me a map, it will do it just like this with some adjustment. So we can do thousands of junctions in Hong Kong because we use a very simple, this is a simulation. You can see when the traffic turn green, you can look at here. The queue is going back. When the light becomes green, the queue disappears. Darker the color meaning higher traffic density. So you can see traffic is moving. This, by the way, is a real Mongkok network. The first example we coded to show to TD, saying that I can do very detailed. And then we put it into vSim. This is the same network coded in vSim. Now in vSim, we can do a lot of work. You can do bus line, we can do a lot of things, you can do pedestrian. So what we do is optimize in DISCO, simulating vSim, show to government that, look, our results are very similar. Okay, this is what we did. To convince people that the model, even though it looks simple, but it captures all the important features. So every time when we implement something, we always show government vSim. Look, this is what we expect to see. So this is always part of the loop, software in the loop system here. So you can, it's actually this model we spend quite some time. We put all the bus lines, all the minibus lines, all the pedestrian crossings, everything we know is inside this, is actually Mongkok area. And this is the example, I say, this is the real-time adaptive system implemented in Dongchong area, for those who know Dongchong. MTR is somewhere here. So you can see small things moving. Actually, this is a real-time adaptive control system first time implemented in Hong Kong by our team. So it's dropped the delay quite sizably. It's just take the traffic data real time and then adjust the signals by itself. And then we actually also develop a measurement method, first time for Hong Kong also. How do we measure adaptive traffic control delay? So we built a manual for TD now. So any system apply this calculation, you can get the performance. So this is basically done in Tung Chung area. And this is the Long Fu Lo. The colors are our computer simulation. We want to track the turning movements. A certain color refer to a certain type of directional change. So we look at, so red in this case going straight, curve around. Blue is, so we know how they turn. And this system is actually also now implemented in Tung Chung. If you drive from Tuen Mun to airport, you will hit a junction here. And we cut the delay quite sizably. This is the first thing is in Bok Fu, Bok Oi. It's also done there. So it's a very big improvement in the delay. Now, these are other projects using the model. This project is also real. This is basically in Kwun Tong. So we talked to the police say, oh, I'm interested. And one time I talked to the fairly high up in the police. They said, this is Hoi Yun Do. You know Hoi Yun Do? Some of you may know, some may know. This is Kwun Tong, Hoi Yun Do. Very congested area. This is the roundabout. And then the police, one time we chat over some meeting, I forgot what meeting. He said, the regional commander saying, every PM, they said now 90 traffic police and warden to kick out traffic in the area. I said 90. That's a lot of resources. I said, maybe I can help you. So we coded everything in there, and then we designed, this is the police car. We look at how police car change behavior. Once you park a police car, all the illegal parking here is gone. But that doesn't last for very long. Only lasts for about a few minutes, and the vehicle will come back. Once the yellow car gone, this is a yellow car, is the police. So we collect data to look into how police change traffic behavior, and we coded that. So you see, later on when you see this car is gone, the police, then all this traffic will start illegal parking again. The cycle is about 3 to 5 minutes. So we capture this and model it. And then we optimize also the signal here. Because if you send police car at the same time, you kick out all the traffic at once. It jam up the region, actually worse. So we say, why don't we design a route for your police to kick out cars in the region? And then when we optimize both the routing of the police, kick out vehicle, and the signal, improvement 15% traffic delay. More importantly, instead of 90 police officers, they sent only 6. Because they track along a route. The police officer simply walk along a certain pathway. I won't tell you it's a police kind of thing. It dropped manpower usage from 60 to 90%. So they're so happy because they release up another 55 police officers to do some other thing. So this is 2023. And then because of that, they asked us to look in the Wong Dai Sin area. Same topic. We cut away 60% police manpower and dropped the delay by about 10-15%. So they're very happy. They give us another project. This project is being implemented. This is a real-time system. So this is the Kwun Tong area. So we build a real-time system that link everything to camera. So if the police point to here, click, they can see traffic here. Let me show you. So this system is now stationed in the Kwun Tong Regional Kowloon East Control Commander Center. So when you click, I can show you the video. So whenever we click on the side, you can look at side. And then we also put AI detection zones here. Whenever the detected zone is covered by a stopped vehicle, it will trigger an alarm to the police. And then we also recommend procedures to take care of that, either changing signal, either send out some policemen. So we did that so we did a lot of detector zones in the area, and it's an event-based trigger control system. Now we are about to roll out this system in Guntong. This thing will save even 6. Now they don't need to send out any police officer. They only send out when it's triggered. And then we also talk to TD, so the timing plans will change according to the traffic pattern we detected. So this thing, we talked in a few months. This system will roll out in the Guntong area. So we are very pleased with this kind of real-time detection system. This is even bigger now. This project is because the police is very happy. So this is, if you know, this is a Kaidak area, the Kaidak sports ground. Last year this time, the Kaidak sports ground was about to open, and government was very nervous. Can they handle 60,000? So police, 6 months before the opening, talked to us. We want to have a very detailed analysis of the crowd. So they do the stress test, you remember. 10,000, 20,000, 30,000, 40,000. So every event, they ramp up. So we send a team to do a lot of surveying and look into the traffic analysis. So by the time when the sport ground was open in April or May last year, we knew it's okay because we already fixed how the bus routes should go, how the signals should be timed, where the loading zone. So we know that because it's already tested. So the police is very happy with this. And then they gave us another project. This is a huge project. This is about 14 million project. So we will do the entire region now. This is Kaidak sport ground. So we look into this whole region as an AIoT online simulator for mega event traffic management. Anytime when they have a mega event, this system will be activated. So we know everything about the region, crowd management, traffic signal, and everything. So this thing, I work with a computer science professor. He will do the AIoT bit. I will do the traffic bit. So this is done by computer science professor. I work on the traffic simulator. And now this thing has become a trend. And the police talk about, why don't we work on Central? What about Happy Valley? So and then yesterday, there are other opportunities come up. So we are very pleased that this become a real-time implementable system. Other applications, we did many demos. Causeway Bay, Mongkok, Zhongguanou area, Kowloon Bay, a lot of demos. So sometimes we use a demo to show people what can be safe. This should be my final slide. Exactly 40. So in terms of traffic, dynamic traffic modeling, I only talk about this piece, which is a disco. Actually, when you think about traffic modeling, there are other pieces. This is the thing we did for, you can see pedestrian moving. This is how we model the Kaidak sport ground. Not evacuation, but when the event stops, where do people go, how long they wait in the bus line, and so on. So we know that Kaidak can handle 60,000 because we already model everything. And then we tune the signals, we tune the bus routes, we tune where vehicle can stop and cannot stop. So everything is already premeditated. So now this is working really well. We also work with MTR on this project. For MTR, their concerns of ridership. How should they increase the frequency of their trains and so on? So we work with both MTR, police, and TD on this. This is what I talk about. This is another simulator here. You can see tiny dots there moving. This is a macroscopic simulator. I put 4 million, the entire traveling population inside this model. So you can see the dots moving. We use that to help MTR plan for their service planning. This is very detailed, second byte, so you can see a simulation clock. You can see a lot of things are happening, like ants, but you can zoom in to look into every train loading, every vehicle occupancy. So we look at that, we call this a Maxim, very detailed microscopic simulator. So we use it to analyze our tunnel tolling, the 3 tunnel tolling. Now it's working really well. We work with MTR on their service planning, which line should be open. and how do they handle disruption. So this is the second piece. The last piece, very recent, is this piece. What is this? Like blinking. We got another project from the government on this taxi. We now can have 2,000 taxis that upload their GPS every 5 seconds. And eventually we have 6,000 taxis. And then we use the taxi data to estimate the travel time. We find that we are very close to Google. So this will open up tremendous opportunity for Hong Kong. So real-time traffic measurement, we can actually do it using taxi GPS location now. This is actually real. So we are still working on this particular project. So if you think about the whole set, we have real-time travel time information. We have macroscopic, 4 million agent, kind of very detailed simulation. We have the traffic signal, we have pedestrian. I think that we have the whole set of instruments for thinking about dynamic traffic modeling applications. With that, I should stop here. Thank you.